Okay, good evening everyone. So I welcome you all to the seventh live session of the NPTEL course on deep learning. This course is provided by Professor Prabir Kumar Biswas, who is a professor in the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur, and myself, Arka, will be an NPTEL PMRF PA for this course on this particular semester. So today we'll be solving the week 6 quiz, and followed by that we'll also be taking up some practice questions for week 7. So in week 7 we have seen the variety of autoencoders such as denoising autoencoders, sparse autoencoders, and we also have seen what is basically meant by convolution and cross correlation. And in the next week, already I think week 8 is also live. So week 8 content is also there in the week website. So from now on, we'll be starting the main deep learning framework. So after doing the convolution, we'll start with the convolutional neural network and the variety of the convolutional neural network. And there will be many things, for example, generative adversarial neural networks, then semantic segmentation and all. So from this particular week, we'll be starting the main deep learning thing. So let us start with week 6 quiz. So the first question is, which of the following is not true for PCA? So, uh, so the first option is rotates the axis to lie along principal components. So can anyone of you tell me that whether this one is correct or not, and with reason why? If it is correct, then why, and if it is not, then also what is the reason behind it? Is anyone? Yeah, am I audible? Hello.
I think principal components are orthogonal.
Yeah, principal components are orthogonal because the covariance matrix is symmetric, so the eigenvectors will be orthogonal to each other. So, but the point is that whether the principal
So
component
it will not
analysis.
rotate. So it will not rotate. The
No,
axis.
no. Let me give
So
you a
option
visual.
D is eigenvectors describe the length of the principal components.
So I'm asking that whether option A is correct or not, and if it
Oh,
is not correct, then why? Let's say you have a data like this. So let's say you have a data like this, distributed like this. So you have x1, you have two features, x1 and x2. So I have restricted myself to drawing only 2 dimensions. Otherwise, I could have shown you 3 dimensions as well, but it would be difficult to visualize. So over here, in case of in this particular image, so can any one of you tell me that whether these two features that what we have plotted over here, are they dependent on each other or not? From the figure, this particular distribution, can you comment about whether the features are dependent or not?
they are, sir.
Yes, they are dependent, as because, for example, the I cap and J cap, these two, you can see that these are orthogonal to each other. So whatever data you plot in the x-axis, let's say whatever data is there in x-axis and whatever the data is y-axis, if you plot these data, so you can see that the data which are basically following in the original axes, as because they are perpendicular to each other, therefore they are not correlated or they are not dependent on each other. However, when you have these sort of data coming around over here in the uh, space which is not basically including the axis only. So over here you can see all the data, they have some kind of dependency. So over here also you can see that these two axes, these two data representation, when we plot the data, so you can see that they contain uh, the areas like this part. So you can see that obviously there will be some sort of correlation in between these two data. Now what PCA basically does is PCA tries to generate the principal components or the orthogonal components in the direction at which variance is maximum. So over here you can see that variance in this particular direction is maximum, and the second highest variance is in this particular direction, the variance is maximum. So what PCA does, PCA tries to create or tries to extract the orthogonal dimensions, orthogonal. So this could be one. Yes. Popularity for our engaging approach to Indian history. Someone's mic is on. So over here you can see that in this particular direction, the variance is maximum. So this could be one PC after you do all the what you call covariance matrix extraction followed by eigenvector calculation. So you will get one eigenvector following this particular side and another eigenvector which will basically follow this particular side. So now you can see originally your data x1 and x2 which were having the dimensions like this, and over there you can see that the data was coming along at the middle part of the coordinates, and hence there was some sort of what you call uh, uh, some sort of dependencies were there. However, when you apply the PCA, you will get the axes. Now the axis will be from this particular axis. Now you got the principal components lying in the orthogonal direction to the whole data distribution. So now you can see these are the current axes what you get after PCA. So when you do the PCA, for example, in week's lecture also, you've been given the problem. You have 4 data points. First, what you do, you try to plot all these 4 data points. Then you do whole PCA calculation, and then you try to draw the vectors. Then you will see that your axes, what was there initially, they will be rotated along the direction in which the variance is maximum. So PCA basically does give you the rotation of axis. That is true. So second one is option B is it is calculated from the covariance matrix. So obviously in case of while doing the PCA, the you need to have the covariance matrix to be calculated, because from the covariance matrix only you will get the uh, principal components and all eigenvector analysis that will be able to do from the covariance matrix only. So covariance matrix is needed for PCA calculation. Then option C is removes some information from the data. So whether this one is correct or not?
Yes, sir. This is correct.
So PCA does remove the information from the data. For example, if you get these two principal components, so if you want to just take the data projection on this particular principal component line, so you will just be having the data, two-dimensional data now represented on the 1D line only. So these will be your data representation, these orange points. So now you can see from the two-dimensional data, now you got 1D data. So that means you are basically removing some of the data, some of the initial data while doing the principal component analysis. Now, if you choose only single PC, then if you choose, let's say out of n number of PC, you just consider only 3 PCs. So therefore, you are actually trying to reduce the data dimension from the original data. So this is also correct. Now the last option is eigenvectors. Eigenvectors describe
Hello.
the yes.
Hello.
Yes, I can hear you.
Sir, but here it is not given that how many principal component we have chosen. If we take all the components, then this option might be.
So generally, if you choose all the if you choose all the principal components, then you will get the faithful data reconstruction. That is true. But what is basically the purpose of doing PCA? So PCA is widely used for the application of data reduction or data dimensionality reduction. So that is why you have to consider. So this notion that you have to consider, that the question is framed on the fact that PCA basically helps you in dimensionality reduction. So that is why this is the correct information. That is true that as you have said that if you consider all the PCs, you will get the original reconstruction itself, and there will be no data loss will be there. Then what is the need of doing PCA? If you just want to retain the all information again, then what is the need of doing all this covariance matrix extraction, then doing what you call eigenvector calculation and all after if your aim is to get the same data itself. So you have to consider the notion that PCA helps in dimensionality reduction, and hence you basically try to lose the data dimensionality using PCA. So that you have to take, you have to consider in your mind.
Okay.
Okay. And the last option states that eigenvectors describe the length of the principal components. So whether this one is correct or not, and why?
It's not true.
And what is the reason?
They describe the direction of the principal component.
Yeah, so eigenvectors basically show you the direction of the principal component. So there, and what basically describes the length of the what basically gives you the length of the PC? Eigenvector shows you the direction, and what basically gives you the length?
The eigenvalues.
Yeah, so eigenvalues basically show you that at what level the principal component is basically spreaded. So what is the basically variance of the particular data along the principal component, that basically gives that information you can get from the eigenvalue, not from the eigenvector. Eigenvector just shows you the direction of the principal component or the orthogonal components of the data. So out of all these, option D is basically the false statement. So that is what our job is. We need to find which is not true. So over here, option D is the correct one. Okay. So the next question states that what is the dynamic range of sigmoid from 0 to infinity? So probably in the last session we did this particular problem. So what is the dynamic range?
It is C. 0.52.
Yeah, so at 0, if this is basically the sigma of x and you vary x in this particular direction 0 to infinite, at 0 the value is 0.5, and as you go along in infinitesimally distant, so you will get 1. So the option is 0.5 comma 1. So this is the correct one. Okay. Okay, so in this particular question, it is stated that zero bias autoencoder has 3 inputs, 1 hidden neuron and 3 output neurons. Yes. Yeah. If the network is perfectly trained using an input 235, what would be the values of the weights in the autoencoder? So what does this particular line mean? Anyone? If the network is perfectly trained using this input value. So what does the perfectly trained phrase means?
No bias.
No bias. No bias.
No bias.
No bias is over here. That means zero bias or no bias. What is the meaning of perfectly trained?
The output
It can
matches with
reconstruct the output
Yeah,
perfectly. Input
perfectly.
matches.
Yes. That is the meaning. So let me illustrate this. So this is your autoencoder structure. So this is the decoder WD, and this is your encoder. So WE basically means the weight of autoencoder, weight of encoder, weight of decoder. Now the question states that you have three inputs. So 1, 2, 3. So you'll have three neurons. The hidden layer has single neuron, and the output layer also having three neurons. Now in the input, you are basically feeding a value. Let us consider this is X. So you are feeding 2, 3, and 5. So you are feeding over here. Now, the autoencoder, you feed it to the input layer, it will go to the latent space. You will get something, let's say L over here. The representation is L. Now, at the output side, let's say the output is represented by O. So what is the loss function of an autoencoder? Or what is the basically job? So it basically encodes the input. And what is the job of the decoder? After encoding the input, what is the job of the decoder?
Decodes back the input. At
Yeah,
the output
decodes.
level.
Yeah, it tries to decode back the input itself. Now, by the phrase perfectly trained means the output should be exactly equal to X. Then only you can say that this is perfectly trained. Perfectly trained means that your decoder should be very efficient, that it is able to produce the input input perfectly. That means output should be equal to the input. So this is what perfectly trained means. So your main expectation, if you have seen the lecture as well, your main loss function is basically if this is output minus input, MSE, or MSE between output and input. So what this basically means that you are trying to minimize the error between the output and input. And if your model is trained very well, so then your MSE will be very low. It will be very low. And very low means what? Very low means O and X, if these two are exactly the same, so then you will get a MSE of 0. So that is what our aim in while training the autoencoder. So that means in this particular question, by putting the perfectly trained phrase, it basically means that output should be exactly equal to input. So that means your autoencoder or your decoder of the autoencoder is basically able to produce the exact replica of the input. Okay. So this is the meaning of this particular part. Now we need to find, to create O equal to X, what will be the values of WE and WT. Okay. So in this particular case, this is very simple. So over here, you can see that your input data has 3 dimensions. So R 3 cross 1. The latent space is having single neuron. So the dimension will be 1 cross 1. That means a single scalar value. And again, the output is having 3 neurons. So the dimension will be 3 cross 1. Okay. Now let us start writing the equation for this particular option, this particular operation. So over here, you can see that L is of size. So even though I know that you all know how to do the matrix multiplication, but let us still write it from scratch. So L is of shape R1 cross 1 and your input is of shape 3 cross 1. So
Sir,
the,
question.
yes,
Sir,
yes, please.
here they have not specified about the activation function. What is that? So will it have impact like whether they
No,
are
no,
using
no.
sigmoid or tan H? No.
No, if they have not mentioned anything, so you don't have to think about the activation and all. Okay, so you just here the main funda is that you have to do the matrix multiplication. If they have explicitly mentioned that they have used sigmoid or some other activation, and as far as in the final exam also, when you will see the questions, if they have specifically mentioned, then you will do the computation accordingly. Otherwise, if they have not mentioned, so my recommendation would be don't bother about the sigmoid and ReLU and whatever it is.
Okay.
So
Okay, sir.
in this particular question, they just want that you just carry out the matrix multiplication. That's it. Okay. So as you can see that L is of shape 1 cross 1 and your input is 3 cross 1. So after the multiplication of weight and input, so weight should be arranged in this particular fashion 1 cross 3. Then only you will get a value 1 cross 1. So that means the multiplication to get L will be equal to WE transpose X. So this is the equation to get the value of L. So now your input is X. So let me write X 2, 3, 5. And your output, if I have to calculate the output will be equal to, output is of shape 3 cross 1. Output is of shape my. Yeah, please turn off your mics if you have nothing to ask. Otherwise, every time I have to just go back and mute yours. Okay, so what I was discussing, yeah. So output is of shape 3 cross 1. Now to get an output of shape 3 cross 1, you have to multiply this WD and L. Okay, so how you will do this particular multiplication? So your WD multiplied with L, directly you can do it. So L will be shape of 1 cross 1, and if WD is of 3 cross 1, then you will get this particular multiplication to be done. So your output will be 1 and 1 will be cancelling out. So the final output will be of shape 3 cross 1. So now let us try to see which of the option basically fits. So again, as because this is very small example, and in the final exams also, they will not give you much very big problems to solve, because you will be having only 2 hours to solve the questions. So the questions will be of similar fashion. So they will be not very hard to compute. So let us now start with option A. Okay, so option A. So in case of option A, what will be the value of L? So 1, 1, 1, you multiply with 2, 3, 5. So what will be the matrix multiplication output? 2 plus 3 plus 5. So if I add them, so it will be what? 10. And now if I calculate O will be what? O will be WD. So WD will be of shape 3 cross 1. So let us write WD is 2, 3, 5. and you have L over here. So you multiply L. So now what will be the matrix multiplication output? It will be 20, 30 and 50. So is it doing the perfect training? So from this particular output, so please comment that whether this is a result of perfect training or not.
Not a perfect.
Yeah, so this is not a perfect training as because you can see that your input was 235. Now you are getting 20, 30, 50. So it is not the replica of the input. So option A is incorrect. Okay, so let us search for option B now. So in case of option B, again, I need to calculate the value of L first. So to calculate the value of L, it will be 111 and like again 235. So the output of L will be 10. Now let us calculate the value of O. So now to calculate the value of O, we need to multiply WD with L. So what is the value of WD given over here is 0.2, 0.3 and 0.5 over here. And you have to multiply it with what? L. So L value is 10. So now you can see 2, 3, 5. So now are you getting the perfect training condition over here in this case? Option B.
Yes, sir.
So now you can see that you've been given the input as 2, 3, 5. And after doing all these particular operations, getting the latent vector and the output, your output is basically the replica of the input. So now you can see that output is equals to input. So this condition is basically satisfied by the meaning of perfect training. So option B will be the correct one. So in other cases also you'll see that if you compute all these things, you will see that you are not getting the correct option. That means you are not getting this particular condition. O is equals to X or output is equal to input. So any further query in this particular question? Yes, any query?
No, sir.
Okay. Okay, so this kind of problem also we have done in the previous class itself, but still let us solve this one. So a single hidden and no bias autoencoder has 100 input neurons and 10 hidden neurons. So what will be the shape of output neuron? Anyone?
Hundred.
Yes, 100. So this is your input layer. Input layer. This is your hidden layer. So hidden layer is of shape 10 hidden neurons. So it will be of R10 cross 1. And in case of autoencoder, you know that after you encode the data using an encoder architecture, you need to decode it back to its original shape. So initially, what was the shape of input? 100 cross 1. So the output layer will also have the same shape 100 cross 1. So this is by the decoder. Now you need to calculate the total number of parameter over here, and they have considered that there is no bias in the autoencoder. So what will be the total number of parameter in WE autoencoder will in the encoder part? Total parameter in encoder?
100.
Encoder would be
10.
100 cross 10.
Yeah, this will be 100 cross 10. And similarly, in case of WD, it will be
10 into 100.
10 into 100. So over there, you can see this is 1000 and this is also 1000. So total number of parameter is 2000. Okay. So the next question is y is equals to minimum of a comma b, and they have given a condition that a is greater than b. So what will be the value of y from this particular condition?
B, y equal to B.
Y equal to B.
Yes, yes, yes. So y equal to b, as because you can see that a is having the highest value and your function is basically the minimum function. So it will be b only, y equal to b. Now the next part is very easy. So you need to calculate dy by dA. So you can see that dy by dA will be equal to 0 and dy by dB will be equal to 1. As you are your y is basically dependent on b, so you will get the derivative existing for this particular option. However, in case of dy by dA, the output will be 0. So option B is the correct option. So the next question states that you have two vectors a and b, and they form the first two principal components after applying PCA. Under this particular circumstance, you need to find the value of n. So what is the property of the principal component that they follow? If A and B,
Dot product
yeah,
is 0.
yes, dot product is 0. So main property is basically PCs are orthogonal to each other, orthogonal to each other. Therefore, you can say that the dot product between these two vectors will be equal to 0. And now you can compute the dot product. So it will be 2 multiplied with n. So 2n plus 4 multiplied with 1 equals to 0 over here. So it will be n is equals to -2. So option D is the correct option. So in this particular page, do you have any confusion for all these three questions? Or otherwise, I will proceed with the next one. Yes, any query for these three questions? Okay, so I hope.
Hello, sir. Last question.
Yes.
Sir, given vector will be a perpendicular to each other in
Yeah,
PC.
so,
Should be perpendicular to each other.
Yes. When
Principal
you principal components, let me tell you. So before computing principal components, what you get is a covariance matrix, right?
Yes, sir.
So this covariance matrix is a symmetric matrix. And how do you get the principal components? By extracting eigenvalues and eigenvectors from this covariance matrix, right?
Okay, sir. Okay.
So you take the eigenvectors and eigenvalues from this particular covariance matrix. And there is a property is there. If any matrix A is symmetric matrix, their eigenvectors are orthogonal to each other. Orthogonal to each other. And now, as because the eigenvectors are orthogonal to each other and we name them as principal component, so obviously they have to be orthogonal to each other. And over here also in the first question, I showed you that if this is the PC1, this is PC1, this is PC2. So now you can see that there is a perpendicular reference is there in between these two. So they have to be orthogonal as because the covariance matrix itself is symmetric matrix, and for any symmetric matrix, the eigenvectors are orthogonal to each other. So that is why PCs are PCs basically follow this particular rule: A dot B equal to 0.
Okay, sir. Okay.
Hello.
Yes.
Okay, sir. Actually, the A comma B are principal PCs.
Yeah, they have said that if you read the question, let's say vector A and B forms the first two principal components. So that means A and B, these two vectors are principal components. Now
After PCA, okay.
Yeah, after applying PCA.
I'm thinking we are applying PCA on these two.
No. There is a vector there. Sorry, there is a matrix sigma. So you do PCA over there. You take PCA.
That's why I did mistake, sir. I was applying PC on these two things.
No.
So then I was thinking, doing long derivation, I was unable to solve this, sir. Okay.
So after applying PCA means there is some vector, you do PCA, you get these vectors, and these two vectors are principal components.
I know this property, but I answered all
Ah.
9 perfectly, but this I did mistake because of
Interpreting the question. Yes.
So okay, sir. Okay, thank you. Okay. Sir,
Yes,
in the
someone.
exam, they will give this much difficulty. The first few questions are no. Before this question, those are little difficulty. We
So
have to remember.
I think
These are,
these particular questions you are asking about.
we have to remember formulas or something because in back propagation it is required like that.
So I would say that don't remember the formula. Try to just derive the formula. Derive
It takes
basically. It takes some
takes
time. It takes some time, but probably in the final question, you might see some of these kind of questions. Not much, uh, but you'll see 2 to 3 questions like this because they have to cover the back propagation area as well, and whatever question they will form from the back propagation. So I think you will see 2 to 3 questions based on neural networks, and you'll be asked to do the back propagation. So you might find some of these types of questions.
So one final kind request, sir. Can you guide us before exam? How to prepare before exam? Because now I have to appear 4 NPTEL for my coursework, PhD coursework, 4 NPTEL exams.
Okay, actually the thing is that there are two sort of TAs are there. One is like us who are taking the live sessions, and another set of TAs are who are actually handling the website, and they are actually putting the quiz questions. So these are two independent sets. We don't know that who is basically putting the question, and they also don't know that whether we are doing this particular sort of NPTEL live sessions or not. Anyway, they will get to know as because our videos are there in YouTube. But we basically don't know that who are the TAs who are putting the questions. So as because these two are independent sets, so I really cannot tell you that.
Questions no, sir. Questions no. With the past experience of the question paper, so how to prepare? What level we how to prepare? So which way is a good? Because we have preparation also will help, no, sir.
So entirely most of the cases you will see numerical questions. That is for sure, and some of the questions will be like the first question. Okay, so you need to analyze between the given what you call given statements, and probably you will also see. So this particular question was option D only was the correct option among all 4. So you might see some questions which might have 2 or 3 correct options. So that is called multiple select question, MSQ. This one is MCQ. You might see MSQ types of questions. And also you might see NAT type of question, that is numerical answer type question. So in case of numerical answer type, what you have to do is basically, for example, over here you are ticking in 0,1, right? So over there, it will be like you need to calculate dy by dA, which will be equal to dash. So over there, you have to write the exact value. And if it is a decimal based question, so over there you need to maintain at least precision up to 2 decimal places. So most of the questions probably it would be numerical only. So that is why I request all of you to get your hands dirty with the Gate online calculator, because in the examination hall you will not be allowed with the traditional scientific calculator. So they will not allow. They will provide the on-screen calculator, and the on-screen calculator is basically a Gate calculator. So you can download any software that is available in internet, and I would recommend you to start using that particular calculator because that calculator is a bit tricky. if you just see it for the first time in the examination hall, you might get intimidated with the working of that particular, because generally what happens is that, let me give you one example. For example, in case of let's say you try to calculate the value of sine 90. So generally in normally in calculator, what we press first, we first press sine, then there will be a box, then you go to that box and you fill the value 90. But in case
There
of
is nothing.
on-screen calculator, it is just the
Nothing.
reverse. It is just the reverse. First you have to write 90, then you have to press sign. So this might seem to be very easy. What I'm talking about, this kind of difficult or something. Nothing is difficult, but in the examination
Mark
hall,
test
this.
will be there. Mark test.
Sorry.
Mark test. We can
No,
appear
no,
mark
no,
test.
no. There is
NPTEL.
nothing like mock test and all. At least I don't know any such things. So probably there is no mock test and all.
How to
There will
know,
be.
sir, exam? How to know exam? How they are giving the calculator and all those things? It will be difficult.
So generally what happens is that this will be an online exam. So you have to go to the center and they will give you the PCs. Okay. So in the computer, you will just have an access to the screen. You just can go to the next page or revert back to the previous page, and there on the top right hand or left hand corner, I just cannot recall it exactly, on the either top right hand or top left hand, you will have a calculator sign. So from that calculator, it is almost alike to gate examination, how gate examination is basically conducted.
Sir, one thing, sir, I am seeing your explanation. It is very great, sir. I am also, I have a teaching experience 6. I am also working in some university, but you are putting your lot of knowledge while you are explaining, other than all NPTEL explanation.
Yes, sir.
Yes, sir. Thank you, sir. Thank you. I'm seeing your motivation to teach a lot, sir. Okay, sir. I have seen your research paper also. It is good. Okay.
Thank you.
Okay, sir. Okay.
Yes, someone was saying something.
100% true, sir, what he said. I also like to attend the class because of you only.
Thank you. Thank you.
Sir, can we communicate for other works to do some research or other kind of works? Can we communicate other than this medium?
Yes, if you have any query other than this particular course and all, for example, if you have any query regarding like in research area or something as well. So my website is I think
I saw.
yeah.
I saw
So
your website.
in my if in my YouTube channel also, if you go to the YouTube channel, you will see my website link is also there in the description. So you can go there and all my contact details, mail IDs are there. So you can mail me. Obviously, I will reply back.
Okay, sir. After coursework,
Sir,
no, we
from
will
where we
discuss.
get your mail ID?
Uh, you can go by either you can go from Google Scholar. So just type my name.
எழுதுல.
So you just type my name with Google Scholar. So the first entry, there is this PM Prime Minister Research Fellow. So this you click over there and then you can. So this is the home page. Let me just increase it. So this is the home page. You just click it over here. You will be directed to the website itself. So from website, you will get to many other contents as well. For example, my previous NPTEL courses content. So everything is online. So you can also access those also. And in the contact tab, you will get the mail IDs as well. So you can mail me at any point of time. Surely I will reply.
Sir, even
Thank
I
you,
want
sir.
to also contact regarding research. Even So, but let me complete this course in deep learning so that I can discuss with you regarding research work.
Yes, sure, no problem.
Sir, one more doubt, sir. I have used that TCS ion calculator for calculations.
Yes.
And I didn't get for finding the exponential value. Actually, I got confused how to use it.
Okay, so
For
actually,
sigmoid function, yeah. So,
yeah, for sigmoid function you are talking about, yes.
yes, sir.
What I would suggest is that you can check any of the YouTube. There are plenty of YouTube videos are there. Okay, so first you check the YouTube video. If you still not able to figure it out, then just drop a query in the what you call forum, in the NPTEL forum. And then on the next session, probably I will just show you some basic calculation using that particular software, because I used the software long back. So I also forgot that what are the of functionalities it has. So I also have to check once. So if you can check any YouTube videos. Otherwise, if you still find some problem, then you can just post your question over there. I will take one short tutorial for that as well. I hope that is
Okay, sir. Okay, sir. Let me try it first. Then next week I'll.
Yeah. On the next week, if you have any problem, just post the question in the forum so that I get notified for the same, and then I will take a short tutorial for that as well.
Okay, thank you, sir.
Okay, so let's move to the next question.
Hello?
Yes.
Sir, in the last question,
Yeah, in the last question, this one.
sir, the covariance
verb-
factor always in general.
Sorry, your voice is breaking. Can you just repeat again?
Sir, actually this question, no, I am
Yes.
confusing meaning, sir.
Okay.
This question meaning I am confusing, sir. This English is not
Probably
proper.
it is not proper, but the meaning that they are trying to convey is that A and B, they forms two first principal components. So this
After applying the
yeah.
PCA, they are
So
telling.
this
We are
particular
applying piece. We
this
are
this
applying.
particular part would be more clear if you put a comma over here.
Huh,
So this
sir,
would put
this should be.
this would put a thrust. So there is probably some typo mistake is there, as because as I have told that there are two sets of TA. So
But
one
they have to
is
give marks, sir. Otherwise, na, we will lose 10% of marks in this one.
okay, that I cannot.
No, you convey, sir. In Python, na, they have given like that only because there are a lot of wording mistakes are there in the question, sir. You just convey to them who are there because it will be otherwise we will convey otherwise because
One thing you can do, you can also I will convey, as well as you can also put the query in the forum itself, or the Q&A bar is there in the website. In the course website, you will find in the task bar Q&A. So what there you put this particular anomaly to remove the typo mistake and all. So yes, this particular line is kind of misleading because many people can thought of that A and B are, you need to do PCA on A and B and then you will get. So yes, you can put the question. Otherwise, I will also try to convey this particular same.
yes, sir. Thank you very much. Okay.
Yes, someone else was saying something. Yes. Yeah, you are audible, but in between your voice is breaking. Can you type your question? See whether you can type your question or not. Now can we see that whether you can type your question or not, or Q&A is there?
No, sir, no.
Yeah, you can go to Q&A. So you can see that there is a Q&A bar is there. In your teams, try to see whether the Q&A bar is activated or not. So after you go to Q&A, you can tap the create post and you can type it over here. Otherwise, you can convey it as well, but your voice is breaking. That is the issue. If you're not able to type, then you can convey it
Am I
over
audible?
here. Yeah, now you're audible. Now you're audible.
Covariance always symmetric in general.
Covariance matrix.
Always symmetric or in general.
Okay. Now I got your question. Okay, so let's say you have a feature which is of, let's say, 2 dimension. Let's say A1 and A2, right? Now, what will be the shape of covariance matrix? What will be the shape? Yeah, what will be the shape of
2 cross.
Yeah, 2 cross 2. So by covariance, what we basically mean is that what is the relation between any two of these entities? What is the relation between, let's say you have extracted from a person, you have extracted 2 features. Let's say A1 is gender and A2 is profession. Right now, the covariance matrix, what it basically gives you is basically the relation between A1 and A2 in different terms. So let's say the first entry or the diagonal entry will be the variance between A1 and let me go to another page as it's becoming clumsy. So A is having 2 features, A1 and A2, and this basically means this particular thing, that A1 is basically gender. You are extracting 2 features from a person, gender and profession. Now you try to calculate the covariance matrix over here. So the covariance matrix, what it basically gives you, this basically gives you the relation between A1 and A2. So the first component is A. So if I write the entries over here, so in the column you have A1 and A2, in the row also you have A1 and A2. So now the first element would be variance or the relation between A1 with A1 itself. A1 with A1 itself. Then the second element will be relation between A1 and A2. The third relation would be, so I'm writing the entries of this covariance matrix. What basically these entries mean. Then the third element would be what is the relation between A2 and A1. A2 and A1. And lastly, the relation between A2 and A2 itself. That means, so these two terms, these diagonal terms, these basically the univariate variance. Univariate variance. And these terms, so in the last class you have read cross correlation. So statistically, that is basically in time domain, if you have 2 signals or 2 images, you can just template, you can do the template matching, it will give you cross correlation. But in case of statistical phenomena, so if you just want to see that whether two events are statistically correlated or not, so for that this is called the statistical cross correlation. So any covariance matrix will have in the diagonal element, it will have univariate variances, and in the off diagonal elements, it will have the statistical covariance, statistical cross correlation. Now, if you talk about symmetricity or not, in case of symmetricity, these two have to be equal, then only it will be a symmetric matrix, isn't it? So if sigma has to be symmetric matrix, these two elements have to be same.
Yes, sir.
Okay. So now in this particular problem, just try to assume, just try to create the physical meaning. So in this particular case, A1 and A2, you are trying to extract the relation or the cross correlation between a person's gender with his or her profession. So you are trying to generate the relation between the gender or his or her profession. And in this particular case, you are basically trying to do the opposite thing. That means you are trying to get a relation between his or her profession with his or her gender. So effectively, you are doing the same thing. So either you are taking relation between gender and profession, else you are taking the relation between profession and gender. So in these sort of cases, you will get the covariance matrix to be same. As well as when, for example, I guess you have some knowledge about MATLAB. If you have some knowledge about MATLAB, then I will suggest you to perform this particular operation. So do you know MATLAB?
Yes, sir.
Okay, so you can use this command co-variance. Okay, co-variance between A and B. So when you do co-variance between A and B, you will get a matrix like this. So this will also give you a covariance matrix over there. So you will see that over here, you will get some entity, and these two entities, let's say A1 and A2. So these two entities will be same. So over there, you can see that how the covariance matrix is calculated over there, and you will see that the covariance matrix that you get from this particular MATLAB command, it gives you the same output. So by that logic, this particular sigma A can be what do you call the symmetric matrix. So if you have further questions, you can ask, or I will proceed with the next one.
Thank you, sir.
Okay. Okay, so now we have a continuation of 3 questions. So that is why I have stacked all these 3 questions all together. So over here, the question is, you have been given a two-layer neural network. So this is an input layer, this is the hidden layer, and this is the output layer. Okay. The weights are represented as follows. So they have given the nomenclature. Weight mn means from previous, let's say a previous layer is k minus 1th layer, and n is a neuron in the kth layer. So there is a connection between m and n, and the weight is basically represented by this thing. Okay. So they have given an example as well. So over here also they have given an example. So the point that you have to take in mind is that sigmoid activation function is applied over here. Okay, in both hidden layer and output layer. Okay, the loss function is basically this one. So this is a mean squared error loss. Okay, so not a mean square, this is a squared error loss. So they have not taken mean over here. So this is a squared error loss. Okay, and T is the true label, right? Now, what you do is basically the initial weights they have given the W1 basically means all the weights of this particular layer. Then the W2 basically refers to the weights of this whole layer. So W1 basically comprises all the weights of this particular layer. So all connections weights have been given over here. Now you need to find output A1 and A2 when the inputs have been given as 1, 0, 1. So over here you are feeding 1, 0 and 1. And along with that you have a bias term over here. So now you have to calculate what is the value of A1 and A2. So one thing is that you can do it by single value. For example, one thing you can do is basically you can track back these weight values and then you multiply with the input and take a summation of them and you will get value of A1. Similarly, you will get a value of A2. Another approach would be you can consider it as a matrix multiplication. So I hope that after doing this particular course, you will be implementing these algorithms in Python or any other language. So if you consider this particular application, let's say after doing this course, you will be doing the real implementation of these particular algorithms. So over there, you will see everything is to be considered as a matrix multiplication. In deep learning, whatever you will do, it will be a sort of matrix multiplication in the intermediate layers. So I am also, let me also try to do it in the same fashion. So I will be considering the inputs and the weights as a matrix, and I will be doing the matrix multiplication to get the final output. That means A1 and A2. So let us consider your A1 and A2 as matrix A. So this is A1, this is A2. So now you can see the shape is 2 cross 1. You have input of shape. Let me first take the bias component. So this is 1. This 1 is for this particular bias. And then you have x1, x2, x3. So that is 1, 0, 1. Okay. Now the shape is what? 4 cross 1. So to get A, your matrix multiplication would be W1 cross X. That means W multiplied with X. So now let us see what is the shape of the W. The shape of W is 2 cross 4 and the shape of X is 4 cross 1. Now you can see what will be the effective shape of this particular output A. Now you can see the after matrix multiplication, the shape will be 2 cross 1. So that is what we want. As because you want A1 and A2. So the shape should be 2 cross 1, and from the matrix multiplication also you can ensure that your output will be of shape 2 cross 1. Okay. Along with that, there is a sigmoid function is also applied after this multiplication, as because you have seen that sigmoid activation is applied on the hidden layers and the output layers. So you need to consider the sigmoid activation as well. Okay, now let us start solving this matrix multiplication. So this is minus 0.4, 0.2, 0.4, minus 0.5. And then you have 0.2 minus 0.3, 0.1, 0.2, and you have 1, 1, 0, 1. So please solve this particular matrix multiplication. And what will be the value after you do the matrix multiplication? Please tell me this one.
Sir, minus 0.7 and 0.1.
Yeah, minus 0.7 and 0.1. Now you are left with calculating the sigmoid function on this particular value. So this will be first one will be sigmoid of minus 0.7 and second one will be sigmoid of 0.1. So you can use your calculator, and as I have also pre-computed the value, so the values are 0.33 and 0.52. So you can use the gate calculator to solve these particular values. And as I have already told that if you find any difficulty, just raise the questions in the next week's forum, and then I will take a short tutorial on that as well. So option B is the correct option. So any further query for this particular question? Yeah, any query for this one? Okay, I hope no query is there because this was pretty straightforward. So this is the continuation of the previous question. In this particular question, they have asked to find the value of y. So you've been given the same inputs, that is 1, 0, 1, and now you've been told to find the value of y. So how you will find the value of y? Now we have computed till this part. Now to get the value of y, we'll be doing matrix multiplication between this one and the weight values over here. So let us first write the, let us consider this one is let's say a hat. So a hat will be, so first component is what? The bias term. So the bias term is this one. And the next component A1 and A2 that we just have computed. So those values are 0.33 and 0.52. And the shape is what, how much? So this is 3 cross 1. And your y is basically of shape 1 cross 1. So whatever matrix multiplication we will do, so the final output should be of shape 1 cross 1 after matrix multiplication. So your weight W2, they have given as 0.1 minus 0.3 and minus 0.2. So this is of shape 1 cross 3. So now I can write y as W2 multiplied with a hat. So W2 is of shape 1 cross 3 and A is of shape 3 cross 1. So now you can see that the matrix multiplication is valid and the output will be of shape 1 cross 1. So now we can proceed with the matrix multiplication. So this will be 0.1 minus 0.3 minus 0.2 and 1, 0.33 and 0.52. So what will be the matrix multiplication output? Is anyone?
Point one.
Just 0.1. So let us calculate it.
You're asking whole answer, sir?
No, I'm not asking the whole answer. I'm just asking what will be the output of this particular matrix multiplication. Just you do the matrix multiplication and tell me the output.
Sir, I got 0.47.
1 second. There in the lobby. You got 0.47.
Yes, sir.
After you have taken the sigmoid activation, or just this matrix multiplication?
No, after taking
So
sigmoid.
matrix multiplication answer is minus 0.103.
Minus 0.103. Yes. So this is what I was asking, that what is the matrix multiplication result? So this is minus 0.103. So, and the last step will be what? We have to
After-
incorporate the sigmoid activation. So you just take sigmoid activation over here, as because you can see that sigmoid activation function is applied in the output layer as well. So after the matrix multiplication, you take the sigmoid. So after you take the sigmoid of minus 1 point whatever it is, so you will get 0.48.
0.48.
So option C is the correct option. Okay. Okay, so the next question states that we need to find del J divided by del W2 1 1. So now back propagation has come into picture. Now, in case of while doing the back propagation, what would be my suggestion is you just try to derive the equation. Don't try to remember the equation. Otherwise, what will happen is that you'll be ending up with wrong equation, and your answer may get you will be marking the wrong answer. So the function that they have given, it is half y minus t whole square. So this is the loss function or the objective function of this particular neural network. They have given this particular loss function. So this is the squared error loss. Now you have to take the gradient with respect to this weight. So the first thing that you have to consider is that whether J is really differentiable with respect to W11. So just by looking at this particular equation that they have given, you will say that no, that I cannot see W11 component in this particular equation. So let me start. Now I have to go for the chain rule. There must be something by which I can do this particular derivative, but I just cannot see the W11 component directly in this particular equation. So it might be hidden inside some other equation. So to do that, I have to do a chain rule to get this particular derivative done. So let me write the other associated equations as well. So let me write what is the equation for y. So y is equals to sigmoid of W012 into 1 plus W02. Sorry. So this will be W11. So W11 2 multiplied with A1 plus W21 superscript 2 multiplied with A2. Fine. Now let me just rename this thing as P. So just let me write it like this. So P is equals to W01 square plus, it is not square, it is subscript. So 1 multiplied with A1 and then W21 superscript and A2. And then let me just write it like this. P of this. So what you get is that first you do all the in this particular neuron. First what happens is that first it happens WIXI. So this WIXI, I have written it as P. Over here you can see that W1 into A1, W2 into A2, and W0 into 1. So that is what I have written over here. After you calculate this linear combination, so here the sigmoid is sitting after this particular linear combination. So this y is basically sigma of p. So that is what I have written over here. First I compute p and then I compute y by taking the sigmoid activation. Now let us start solving the gradient chain rule. So del j divided by del w211 is equals to, I can see that j is dependent on y. So I can do the derivative of j with respect to y. Okay. Now I can see y is dependent on p. So I can take a derivative of y with respect to p. Now I can see p is dependent on w11. So now I can write del p divided by del 11 superscript 2. So if you now see, all these things will cancel each other. So you will end up with del j by del w11 superscript 2. So now you can see that this is the gradient equation, or this is the, sorry, not the gradient equation. This is the chain rule equation that you get while doing the derivative. Now the thing that is basically left with just to do the derivative and put all the values. So let us start doing this solution. So del j by del y. So I will take derivative with respect to y. So the output will be half and 2 will cancel each other. So it will be y minus t. Then del y by del p. So del y by del p. So that means you are doing del y by del p. So this is effectively means the derivative of sigmoid function. So in the last class also I had derived derivative of sigmoid function. So derivative of sigmoid function is what? The final result is sigma p into 1 minus sigma p. And sigma p is what? Sigma p is y. So I can write it as y into 1 minus y. So this is what the dy by dp means. So I can just directly substitute this one. So it will be y into 1 minus y. And the last thing that remains is you take the differentiation of p with respect to w11 superscript 2. So everything will vanish. So this one will go, this one will go. So the final thing will be a1 only. So this is your final answer, that del j by del w112 will be equal to this one. Now you put the values. So from the last question, we got the value of y, which was 0.48. The value of t they have given over here. So t is equals to 1, you put 1. The value of 1 will be 0.48 again, 1 minus 0.48 again, and the value of a1. So the value of a1 we got in this particular question over here. So this is the value of a1. So that is 0.33. So you just put the value 0.33. So please calculate this particular multiplication and tell me what is the answer.
Minus 0.909.
Minus 0.09.
Sorry, 04.
Okay. So yes, so that is the correct answer. So that is minus 0.04. So if you have any query on this particular solution, so you can ask.
Sir,
Yes.
all the time we have to use sigmoid answer.
Yeah,
Before
all
the value.
everywhere, whatever you do. So the last class also we discussed similar thing. For example, the neuron structure, if you see. So let's say you want to calculate the value of a1. So the neuron output is a1. What is the structure of neuron? So the neuron structure is, first is wi xi. So let's say this is W2, this is W1, this is W3, and this is X1, X2, X3. So in this particular part over here in this neuron, in the half part, what you are doing is W1 X1 plus W2 X2 plus W3 X3, which I have enumerated as Wi Xi. Now, after you do this, you have activation function over here. So over here you have activation. So in this particular case, they have said you have a sigmoid. So A will be equal to sigmoid of summation Wi xi. So this is the thing that you have to do. Wherever it is written that you have an activation function, so this is the rule that you have to follow. First, you do the linear combination. That means Wi into xi, whatever weight you have, you multiply with the inputs, take summation, and then you apply the activation function to get the output. So same thing that you have to do over here.
So what
Over
about
here
the loss function? What about the
Yeah.
loss function, sir? Loss
So
function?
they have given the loss function over here. So this is the loss function.
Okay,
So
in the architecture where it is part of, like, it is
okay,
also part.
so when you do the back propagation, what is basically happening is that you are getting, let's say, a y value. So you are getting a model prediction. So that is equals to y. But for example, in your case, let's say in this particular case itself, you got a y value of what? You got a y value of 0.48, right? So in this particular example itself, you got a y value of 0.48. But your original target is how much? The target value is given as 1. That means you are expecting this model should give you 1, but you are getting 0.48. That means you are doing some sort of miscalculation. That means some sort of penalty is there. So now loss function comes at this particular portion. At this particular portion, when you see that there is a substantial difference in between the target, the original one, and your model prediction, that is y. Now you do over here, you do the calculation of loss. So this loss is, they have given the equation, you do loss is equal to half 0.48 minus 1 square. So if you now when you get a loss value, now this loss value should be back propagated. So for that, we have to do this chain rule and all these things.
Sir, in the video lectures also, they are using the sigmoid function for activation.
Yeah, so we are also
Sir,
doing sigmoid as activation only.
Sir, in the exam also, it will be the sigmoid function or some other
Some
activation.
other function. So other function might be there. I cannot exactly say, but sigmoid and ReLU, these two are very quite common activation function that we use. So you can practice some questions with ReLU as well. So in case of ReLU, what will happen is that, for example, it will be f is equals to max of 0, x. So for example, in this particular case, when you are doing, so for example, in this particular case, if I take this, so instead of writing sigma, let's say ReLU 0.-07 and ReLU 0.1. So what will be the output? Anyone?
.1.
Yeah, so for this particular thing, it will be 0.1. 0.1. And in case of this particular case, the output will be 0. Why it is 0?
Yes, because it is max of.
Yeah, it is
0
max of 0, whatever value you put. So for the all the negative values, it will get output 0, and for the positive values, it will return the same value.
Yes, sir. So, but for the chain rule also, we have
Chain
to
rule,
use the
chain rule. When you will do the chain rule, then again this particular part will change. This particular part will change. So over there, it will be 1. If you see that whether your data is lying in the positive half side. If the data is lying in the positive half side, let's say this is ReLU of 0, x, and if x is greater than 0, so y will be equals to x. Now you take the derivative, so dy by dx, it will be 1. So instead of writing y into 1 minus 1, then this will be 1.
Okay, sir. I
Okay.
understood.
So whenever you change the activation function, then you have to bother about all these cases. Like you have to see that what is the effect in the chain rule as well, in the derivative as well.
Okay, sir. Understood. Sir, here we are writing J dot. What is the meaning of dot?
Actually, the J dot is basically the argument. So you can write J of y. So
Okay,
the
sir.
original practice will be the variable. For example, we write na f of x, and then we start writing x squared plus x to the power 3, something like that. So over here, which one of these are variable? The variable quantity is y only. So you can write j of y. So instead of writing that, they just have taken j dot.
Okay, sir. Thank you. I understood.
Okay. Okay, so this is the last part. So in this part, what they have said is find the updated value W211. So the font is so small. So let me write it again. So 212. We need to find the value of this particular weight after first iteration. Okay. So can any one of you tell me what is the gradient descent rule equation? The equation of gradient descent rule. So this is the weight value at first iteration.
The laser W21 minus power 2
Power 2 and 0.
Neta
Yeah.
into dou E by dou J by dou W of 21.
Yeah.
2 power 2.
Power 2. Yes. So this is the equation that we have to follow over here in this particular case. So what was the initial value of W21? So this is the value of W21. So we can see from this particular matrix. So W21 is this one. So initial value of W21 superscript 2. Initially it was it is minus 0.2. So the initial value is minus 0.2. Now we need to calculate first this derivative. Again the same thing. So del j by del W212. So now I can write it directly. Del j, I can differentiate it with respect to y. So del j by del y. Second is del y divided by del p, and then del p. So if I go to the previous slide, so p is dependent on W21. So I can differentiate the p with respect to W21 superscript 2. So W21 superscript 2. So these will have the same value. So it will be y minus t. Then y into y minus y, and over here it will be A2. Okay, now you put the values and just let me know what is the answer for this particular derivative. You put all the values.
0.067.
Minus 0.067.
0.067.
Yes. Yeah. So this is dou j by dou 21 2. Okay. Now you plug all the values over here. So W21 superscript 2 at first iteration. To show that it is at first iteration, I am just writing it in a close bracket 1 will be the previous value that is given, that is minus 0.2 minus 0.2. So this is the point, and then minus. So over here you have eta value is how much? 0.9. So 0.9 multiplied with this derivative value. So this is minus 0.067. So if you do all the calculation, the value will be how much?
Minus 0.139. We have to write as 139.
So minus 0.14. So option C is the correct. So any further queries for this particular question? Yeah, any query for this question? Okay, so I hope there's no further query. So let us quickly take up some questions for this particular week. So you have seen in the week 7 course, there is a neural network architecture that is called stacked autoencoder. So how do you train a stacked autoencoder? How do you actually train the stacked autoencoder? Is anyone? Okay, so this is a sort of example for stacked autoencoder. In case of stacked autoencoder, you stack several layers of encoder and several layers of decoder to make the autoencoder structure a deeper structure. So to get a essence of deep learning. Okay, so now when you stack multiple encoder layers and followed by that you have the stack of multiple decoder layers. So the training would be very much cumbersome. Why? Because you feed an input, then you feed it to the next layer, feed it to the next layer, it will go to the latent space, then it will start reconstructing. And at the output, it will finally fully reconstruct. It will try to reconstruct the input as well. Now, think it of this is the forward pass. That means how the data is passed in the forward direction. Now let us think it in terms of the back propagation. Now when you do the back propagation, if you train the model as it is from scratch itself, so what it will do is it has to back propagate to this particular layer, it has to back propagate to this particular layer, this one, this one, this one, until this one. So that means you can see you have to memorize this much of tensor values. So that means in your RAM or in your GPU memory, you have to allocate this much of variable values. So that means when you do the training of SAE, that is stacked autoencoder, from scratch, then too many parameter you have to optimize. Parameter have to be optimized. That means it requires high RAM or it requires high GPU memory. So to avoid this, what people try is basically they do a layer wise pre-training. What does basically this layer wise pre-training means? So you take this input layer, you take this first layer, you put a decoder over here, and then you train this particular layer. Then you just cut it off. Okay. Now what comes next is you take this particular second layer, and then you do again the encoding, and then you put a decoder layer over here, then train it, and then again cut it off. So that means now you can see, instead of training this whole network at a once from scratch, you are doing the layer wise pre-training. Now this layer wise pre-training will reduce the computation when we'll do the final training. So that means when you do the layer wise pre-training, the RAM requirement or the GPU requirement, that will be very much less. Okay, so let us scan the first option. So the first option state that, so we need to select the correct option. Layer wise, layer by layer autoencoder pre-training reduces the GPU or CPU memory requirements. So this is true. Second option is layer wise autoencoder pre-training alleviates the slow convergence. This is also true. Why? For example, you have to train this big model at once, and you are tracking the loss values. So now you see that this whole big model, while trying to optimize all the weights values at the same time, the loss curve will be very much noisy, and it will take so much of time to converge because this model has to optimize all these number of parameters. However, in case of layer wise pre-training, you already have pre-trained the model. You just have to do the final fine tuning. So when you will do the final fine tuning, it will quickly converge. For example, the loss function will start from this, and then automatically gradually it will decrease. However, when you do the scratch based training, so over there you'll see that it requires too much of time to converge. And convergence means when it basically tries to reach the zero.
ಸೆಷನ್ ಮಾಡಿದೀನಿ ಮುಗೀತದೆ 8ಕ್ಕೆ ಅದಕ್ಕೆ ಹೇಳಿದೆ.
Okay, so layer by layer pre-training of autoencoder alleviates the slow convergence. So this is also true. It basically reduces the slow convergence process. Then third option is layer by layer autoencoder pre-training followed by fine tuning converges more optimal parameters than end-to-end training. So end-to-end training means this one. So from scratch, you train the model at once. So we already have seen that if you train the model from scratch, it converges very slowly. However, if you do the layer wise pre-training, the model converges fastly. So that is what written over here. So layer by layer pre-training followed by fine tuning converges more optimal parameter than end-to-end pre-training. So this option is also correct. So option A, B, C, all three options are correct. So we can choose that option D is the final correct option.
So one query regarding this.
Yes.
If it is layer by layer training, then can we do each layer simultaneously? That is parallelly can be done?
Parallelly you can do, because there are some methods. So this course is basically following the papers, because all these things came just a decade ago. Okay, so the course is basically following the first paper on all these topics. So in the initial phase, people just used to do the layer wise pre-training at once. So they didn't do the parallelism of the training process. So there are now some methods have came by which you can do this parallelly layer wise pre-training. So we are following the papers which came around 10 years ago. So that time people just have did the layer wise pre-training at once. But currently you can see several papers are there which basically claims that they can do it parallelly so that it can reduces the competition.
Audible.
Okay, so one more. So if it is done at once and if it is done parallelly, will there be any change in output?
There might be, because why I'm saying first, am I audible or not?
Yes, you are audible, sir.
Okay. So this might give you some different result. Why I am saying this? So let's say every deep learning model, the main heart of this deep learning problem
Sir,
is.
voice is not audible. Sir, your voice is not audible.
I think I am audible. I think at your side probably some issue is there because others are saying that I am audible. So again, whether I am audible or not.
Yes, you are audible, sir.
Still
Yes,
not
sir, you
audible,
are
sir.
audible.
Okay.
Might be for others, I don't know.
Yes,
Okay.
sir, it's audible, sir.
Okay. So what I was telling is that this might give you some different result because the deep learning model, the heart of the problem is basically the gradient descent rule. So in gradient descent rule, you can see that Wn is W n minus 1 minus eta del E by del W. Right? So this is the gradient descent equation. Now let us go at the first iteration. So when n is equals to 1, so W1 is W0 minus n dE by dW. Now you can see this W0, that means at iteration 0, the value that you assign to this particular variable, you assign this value randomly. Right? So when you assign a value randomly, so for example, I assign a value 10 and you assign a value, let's say 100 or 1000. And as you assigned a value of 1000, you might have got very good result. Right? So at your particular case, when you do the deep learning, so you might be getting a good convergence. However, I am not getting a good convergence. So this might happen, but the gradient descent rule is auto-tuned gradient rule. So this also has a property that it might give you similar kind of responses, but it may not be the exact same. So it might give you some difference, let's say in 2% or 3% accuracy mismatch may be there, but you will not get very significant change. You might receive some change with a tolerance band of 2% to 3% like that. And this basically depends on how you initialize the variable. So if you are doing deep learning, you will see there are several initializers are there. So you can search in internet. So these are called initializers. So you will see there are initializers like he initializer, then glodot initializer, then uniform initializer. So people use different sort of initializer to initialize their weight values, and different initializer will end up in different results. And we hope that this particular gradient descent rule will try to optimize the whole model in a such a way that it will give you an optimal result. But it might happen that your model and my model, they would have they may give you some different result, but with a tolerance pattern of 2%, 2% like that. But it will not give you very significant change in the answer.
Sir, one doubt.
Yes.
Sir, here in the structure, autoencoder only encoder and decoder will come.
Yeah, in autoencoder only encoder and decoder will come while training. Yes.
Yes, sir, yes. Normally in digital electronics also decoder encoder it will come. What is the difference between here and there? How we are using? Why we are using here for encoder and decoder?
Actually that encoder decoder is something else. So over here, what we are basically trying to do is, for example, you have a data dimension, let's say 50,000 cross 1, and in your particular system, you are not able to process 50,000 data in a batch. So you will not be processing one data at a time. You will have a batch, let's say batch size of 128. So processing that big amount of data, so you can consider, let's say you have a batch of 128. So that means you have to process this much of data. So now you can see that how big the data is. and you don't want to process this much of data. What you try to do is you try to reduce the dimension of the input data. So let's say you are trying to reduce it in the order of 500 cross 1. That means you are trying to reduce the data by 100 times. And when you try to reduce the data, what you are trying is basically to learn the intermediate hidden features, of a data. So there is a very good example, but that is a numerical example. Probably in the next class, I can show you what I basically mean by a what is called the uh, hidden pattern inside the data. So for the time being, just consider that while reducing the number of dimensions, your main aim is to understand the underlying hidden features of a given data. And because you are reducing the number of dimensions, your data dimension will be reduced, and which will help in further processing as well. But you have to keep in mind that while training the model only, you have the decoder part. But at the time of testing or at the time of some kind of classification task, if you want to use it, so you will chop off this particular decoder part. You will use this latent vector and you will feed it to a MLP network or any other deep learning network or any other machine learning network. Let it be SVM, let it be Bayes network or something. So you will be using, instead of using this 50,000 shape of data, you will be using just 500 dimensional data, which subsequently reduces the computational complexity in the further process. And you basically get to know the exact hidden pattern that is there inside the big data. So you can see that initially your data was 50,000, and when you have 500 data, that means you have very compressed information. So in autoencoder, we basically try to learn what is the compressed information or the hidden pattern that is there inside the data. So it is pretty different from digital electronics or encoder decoder. That is something else.
Okay, sir. Thank you, sir. Sir, latent space, what it is representing?
Latent space, basically the last encoder layer from which you basically get the reduced dimension data. So let's say over here you have 50,000. You are reducing the dimension to, let's say, 10,000. In the next layer, you're reducing the dimension to 1,000. And in the last layer, you are reducing the dimension to 500. And then again, you just try to generate the same dimensions. Let's say over here, the dimension will be 1,000. Over here, the dimension will be 10,000. And at the last end, it will be dimension of 50,000. So that means till this part, you are encoding the data into 500 cross 1 size. And from here, you are trying to decode it or generate back the original dimension. So this last layer output is called the latent dimension output.
Okay, sir. That means structure and feature, it will be reduced.
Yeah, so your data dimension will be reduced, and at the latent dimension, we'll get the reduced dimension vector.
Okay, sir. Thank you, sir.
Okay. Okay, so have you guys read the contractive autoencoder?
First one, sir, answer. Jacobian matrix.
Yeah, so regularization of contractive autoencoder is basically you have a Jacobian matrix. In Jacobian matrix, what you do is basically you take the gradient of the activation. So let's say the activation is A over here for a particular input X with respect to the input. So that is input component, let's say Xi. Then for all the input, you just take the gradient x1, x2 like that. So you will get a Jacobian matrix, and the Jacobian matrix. So that is what it is written over here. So the regularization of contractive autoencoder is basically applied on or imposed on the Jacobian matrix of encoder activation with respect to the input. So this is the mathematical operation. You take the activation for an given input and you take the differentiation with respect to the input itself. So dA of x divided by dAx1, dx1. So it is pretty straightforward. It is from the lecture itself. You can see the variant of autoencoders lecture, probably lecture 1, and you will see this particular operation there. Okay. So what is so we need to select what is the true statement about KL divergence. So can any one of you tell me what is the formula of KL divergence? KL divergence, let's say between P and Q, what is the formula? Is anyone?
1 minute, sir.
So this is the formula. So P log P by Q. So I can just write it as P log P minus P log Q. So P log P and P log Q. And if I just write P Q by Q by P or Q given P, so it would be Q log Q by P. So it will be Q log Q minus Q log P. So we need to select the true statement. So let us first see option C. So option C states that KL divergence is symmetric. Is asymmetric. It would be symmetric. So KL divergence is symmetric. And that is KL of PQ or KL of QP is equals to same. So I have written that KL of PQ and KL of QP, are they looking same?
No, sir.
No. So that means KL of PQ is not equal to KL of QP. So that means option C is incorrect. This is incorrect. Let us see option A. Option A states that KL divergence measures distance between two probability distributions. So P is a probability distribution, Q is a probability distribution, but they are saying that it measures distance. Distance has a very nice property. Let's say you have 2 points, X and Y, and you have to take the distance between X and Y. So if let me just ask you a question. If I ask you to derive the or to evaluate the distance from X to Y or from Y to X, will they be different? Let's say you are in a Euclid, you are in a Cartesian coordinate, system. So if I ask you to take the distance from X to Y or distance from Y to X, will they be same or not? Distance value from X to Y and distance value from Y to X, are they same or not?
Same only.
Same only. So you can see that distance is symmetric in nature. Symmetric in nature. As far as Euclidean distance is concerned. So we'll be considering Euclidean distance. So distance is symmetric in nature over here as far as Euclidean data is being concerned. So over here, you have seen that KL divergence is not symmetric. So we have already proved in option C that KL divergence is not symmetric as because PQ and QP, they give different result. However, distance is symmetric. That means distance from dxy or distance from y to x, that is same. So therefore, we can say that this is also an incorrect option because distance is something which is symmetric, but KL divergence is not symmetric. So we can say that this line, it measures distance. So this particular phrase is incorrect. I cannot say that it measures distance because distance is something symmetric. KL divergence is something that is unsymmetric or asymmetric. Okay, so option A is also wrong. So last option that is left with is it has a range of 0 to 1. So is it true or not? And if it is not true, then why? So let us consider one of these probability densities or one of the probability distributions is 0. So let us consider P is equals to 0. So if P is equals to 0, what will be the current situation? It will be 0 multiplied with log of 0 divided by Q. So what is log of 0? It is undefined, but you multiply something with 0 over here. So it will give you finitely 0. So that means you can say that the lowest limit of this KL divergence can be 0. So this is fine. It ranges from 0. Now we have to see whether it ranges up to 1 or not. So now let us consider P equals to 0, Q equals to 0. So in this particular case, what will be the current situation? The situation will look like 0 multiplied with log 0 by 0, again undetermined. So you cannot determine this particular function. And let us consider another case where P is finite, Q is 0. So over here you can see that P multiply with log P divided by 0. So you write P log infinite. So log infinite will shoot up to infinite. So P multiplied with infinite. So it will be infinite. So over here I can see that this 1 is incorrect. So KL divergence has a range from, this is range from 0 to infinity. So again, option B is also incorrect. So I can see that all of these are incorrect options only. So these are incorrect. So I can see that none of the above. Okay. So in which conditions autoencoder has more powerful generalization than principal component analysis by performing dimensional reduction? So what will be the answer for this particular question? PCA is a linear transformation, But autoencoder generally we include non-linearity terms. So that is why autoencoder performs better than PCA. But over here, in this particular case, you can see that this under complete autoencoder means you are basically reducing the dimension. In case of over complete autoencoder, either you keep the same size in the hidden layer or in the latent space, or you even increase the size. So you are not at all reducing the dimension. And over here, what they have said, while performing dimensionality reduction. So overcomplete autoencoders first on the first hand, they will be cancelled. Now we are left with option A and option C. So now what they have written that in which case autoencoder has more powerful generalization than PCA. So PCA is a linear technique. So an autoencoder is a non-linear technique. So under complete autoencoder basically reduces dimension. So this is under complete. This is under complete. This is over complete. So in case of over complete, either same dimension or increased dimension to that of input size. So by this logic, under complete autoencoders are already nullified. Now we are left with over complete autoencoders are already nullified. We are left with under complete autoencoders. So in under complete autoencoder itself, we can see that there are two options: linear autoencoder and non-linear autoencoder. If the autoencoder is linear, then it will work alike to a principal component analysis, as because principal component analysis is a linear transformation. However, in case of traditional deep learning based autoencoder techniques, so we use nonlinear activation functions over there, which basically gives you more powerful generalization capability. So that is why this option C is the correct option. So for example, if I show you in terms of a data distribution, you have probably seen this particular example in the week's slide itself. So let's say you have a distribution like this, data distribution like this. If you do a simple PCA, as simple PCA is a linear one, it will approximate it in a line. However, as autoencoder is a what you call a non-linear technique, it tries to capture somewhat the structure of the data in a non-linear fashion. So you can see that instead of getting a straight line, the autoencoder gives you some curvature, so which basically replicates the hidden structure of the input data. So that is why under complete autoencoder with non-linear activation basically gives you better generalization than PCA. Okay. So yeah, so this is a pretty straightforward question. So can any one of you answer this one? Which of the following is used to match template pattern in a signal? Yes, anyone? So let me just give you the correct answer. So this would be convolution does not give you basically the template matching or template pattern matching, something like that. It basically, so you have a signal over here and you have a kernel over here. You just first you try to flip the kernel, then place it at the edge of the original signal, and then you pass it over through this original image. So this is x1, this is x2. So what you do, you flip x2, then you put x2 over here. Let me just draw it like this. You put x2 at this particular place, then you try to slide x2 over x1, and then you keep on recording the final output, and then you will get a graph like that. However, in case of correlation, or specifically saying cross correlation, basically helps you giving the template pattern of the signal. But it is not just the cross correlation. Cross correlation is biased towards the final amplitude value. So in option C, if you normalize the cross correlation by the factor of maximum value or the summation value of the whole kernel size or the maximum value of the whole kernel size. So you will get a normalization factor over there, and that normalization will help you in getting the template of the signal. So let me give you the reference as well. So this particular thing you will get in lecture 35 at 28:49. So you just can see over there. So Professor PKV has also also have shown that how normalized cross correlation basically gives you the what you call the template matching operation. Okay, so here we have to first see that we have to show that which of these four are basically represents the LTI or LSI system. So LTI or LSI system or linear systems basically follow a property that is called superposition theorem. Superposition theorem. So for each and every cases, we have to see that whether all these candidates basically follow the superposition theorem or not. If they do not obey superposition theorem, then we can see that this is not a linear system. So even before applying superposition theorem, I can see that y is m into x square. So x square, is it a linear operation? It is not a linear operation. It's a quadratic function. So that is, it's a non-linear operation. So for example, if I just draw it, so it is like this. So this is a non-linear function, non-linear. So option D is incorrect option. Now let us see for y1 for option B. Y equal to mx plus c. Is this a linear system? Anyone?
Yes, sir. This is the linear system.
This is not a linear system. This is not a, this looks like a equation of a line, but as far
Sorry,
as
sir.
system,
Linear time invariance.
this is as far as linearity is being concerned. So if you try to see the superposition theorem, you will see that this particular system does not obey the what you call uh, this particular system does not obey superposition theorem. I will show you why. So in case of superposition theorem, the main funda is that you apply two different, let's say two different inputs at once. You take the output. So if you apply x1 as an input, so output will be y1 equals to mx1 plus c. Now if you apply x2, so output will be y2 equal to mx2 plus c. Now you apply. So initially you are applying x1 and x2 individually. Now you apply a combination of x1 and x2. So let us consider x1 plus x2. So the output y3 is equals to m x1 plus x2 plus c. Now let us check if I add these two outputs, whether I get the same output when I apply x1 and x2 simultaneously or not. So let me write y1 plus y2 is equals to mx1 plus mx2 plus 2c. However, we can see y3 is not equal to y1 plus y2. So that means if you apply the inputs individually and if you apply inputs simultaneously to the system, the output that you get is not equal to the summation of the outputs when you apply inputs individually. So that means superposition theorem is not valid. So let us consider option B is incorrect. Let us see option A. So in case of option A, you have y equals to m plus n into x. So I just take m plus n as common term, m plus n into x. So you apply x1 as an input first. So it will be y1 is equals to m plus n x1. Y2 will be equal to, when you apply x2 as an input, it will be m plus n x2. So it would be m x1 n x1. It would be m x2 plus n x2. Right now, you apply what you call let's say y final is equals to m plus n, then x1 plus x2. Okay, so you will get mx1 plus mx2 plus nx1 plus nx2. So let me just arrange it in this fashion: mx1 plus nx1 plus mx2 plus nx2. So now you can see that y final is equals to, from these two terms, what will come? It will come y1. From these two terms, what will come? It will give you y2. So you can see that when you apply this input simultaneously, x1 plus x2, the output is yf. And when you apply these inputs individually, and if you take the summation of these two, now this is giving you the same result. So that means when you apply this input simultaneously to the system, whatever output it yields is equal to the summation of the outputs when you apply the inputs individually to the system. So therefore, you can see that superposition theorem in this case, superposition theorem is obeyed. So as it is obeyed, so I can say that option A is the correct option. And option C also you can do it. So instead of plus C, now you got minus C. So it will no longer change anything in the linearity and all. So it will also be nonlinear. So all these cases are nonlinear. Only this particular case is a linear system. So hence this satisfies that option A is the correct option. Okay. Okay, so what could be the answer for this particular question? Anyone? So this is also very straightforward from the week lecture. I have taken this particular question. What is the role of sparsity constant in the sparse autoencoder? What is the meaning of sparse first?
Control the hidden layer. The C, first one.
Yeah, first one. But what is the meaning of sparse?
Applying zeros in a,
Yeah, that means majority of the values that will come out of this hidden layer or the autoencoder layer, majority of these values will be 0. So so that is what basically sparse autoencoder means. Now over here, let's say, so what our aim is basically to control the output of these layers, control the output of these nodes. And as we want to create this sparse autoencoder, that means majority of the output that we want, so that would be 0 only. So our main aim is to control the activation of the neurons in the hidden layer. So let us see. So control the hidden layer length, not at all. Not related to sparse autoencoder. Also, this is not the correct one. So control the number of active nodes. So by active node, what they mean is that the active node will give you some output. That means it will not yield 0. So control the number of active nodes in the hidden layer. So that is what our aim. So our aim is basically to generate most of the value 0. So that means we'll be controlling the activity of the hidden layer nodes. So that is why option A is the correct option. And let us see the option B as well. So control the noise level in a hidden layer. So that is also not the purpose of sparse autoencoder. Sparse autoencoder basically tries to generate the sparse representation of any given input by controlling the activity of the nodes itself. Okay. So this is the last question. So which of the following is true about convolution? So convolution is used to compute features from the signal, whether it is true or not. Anyone? Yes.
It is, sir.
Yeah, so this is true. So we use convolution to extract features from a signal. So you have probably seen that there was an image. So there was some kernels. There were two kernels in the week lecture. So one kernel was like this, another kernel was like this. So when you convolve the a building image was there. So if you convolve this particular image with this, so you will get the horizontal lines. So let's say you have three horizontal buildings. So you will get three horizontal lines. If you convolve it with this vertical kernel, so the output will be the vertical edges like that. So that means this from this horizontal kernel we are getting horizontal feature, and from the vertical kernel we are getting the vertical edge features. So that is why we can see that we use convolution to extract features out of the signal. So the second option is so option A is correct one. Yeah. Option B is can be used to compute cross correlation between xt and yt if input signal is transformed to x of minus t and y. So let's say that the previous thing that I have told, let's say you have two signals x1 and x2 like this. So what you do, let's say you flip x2, you flip it like this, and then you pass it over the x1, and then you will get the convolution. So they have said the same thing. You transform xt into x of minus t. So x of minus t means what? I just have mirror imaged this particular signal over here. You can see that I have just taken the mirror image. So that is why this AG part has come over here. So after that, you slide this particular red or signal or x2 of minus t, you slide this over x of t. So that will give you the convolution. So over here also the same thing is happening, that you first transform xt into x of minus t and then you pass it over yt as a filter. So you will get the convolution. So option A and option B both are correct. So I can say that option C is the correct option. So you have to choose option C. So any questions?
Can we expect any hands-on, sir, on PC and autoencoder common example? It would give better intuition.
Okay, I will try to give you one hands-on session on autoencoder then, because both the things
both.
if I have to cover both the things in the same lecture, it will again take too much of time. So in one session, I will do a short demonstration of PCA, and one session I will do a short demonstration of what you call the autoencoder.
Okay.
So can you just give something about stacked autoencoder?
Yeah, stacked autoencoder is basically, for example, you have several layers of encoders and decoders stacked into your model. So you can see now you have 1, 2, 3, 4, 5, 6. So now you have 6 weight levels, 1, 2, 3 like that till W6. Now these weights are also not single dimensional. They are of multiple dimensions. For example, if your input size is 50,000 over here in this particular input layer, and the second layer is having dimension, let's say 10,000. So yeah, 10,000 is this much. Yeah. So your weight one will have dimension 50,000 cross 10,000. Now, can you imagine you will be optimizing this much of weight by backpropagation? In all the examples, in the questions, they just give you a single weight updation rule. But while doing the coding, you will be doing just for a single W1, you will be updating how much this is, probably 50 million, 5 million or something. So just think in this first layer itself, you have this much of big number of weights have to be optimized. And same you go along with all these layers, it will shoot up to a very huge number. Now training this whole model from scratch in an end-to-end fashion, it will be very difficult because every time you have to backpropagate, you have to remember the previous activation value, you have to backpropagate again, you have to backpropagate to the previous layer. So that means you need a very huge memory to save all the values for a single backpropagation. That means it will require so much of RAM size. And the convergence will be also very slow because it has to optimize all this much of weight value simultaneously. So that means in one iteration, you might be getting very good loss. In the second iteration, you are getting very high loss. So that means again, your model has to go for the back propagation. Again, it will compute all the forward pass, then it will go for the back propagation. So it is a very prolonged process. So to alleviate that, so researchers propose that why don't we train a single layer at a time, then we'll stack all together and then we'll do a fine tuning. So that is basically a stacked autoencoder means. Unlike a full scratch autoencoder, when you train it in an end-to-end fashion, which will basically take so much of RAM space, have lower convergence rate. Instead of that, people try to pre-train each of the layer at a time, then stack all together and then do a fine tuning. So this fine tuning will basically help you in faster convergence. Now you can see that you already have trained these models, trained these layers. So you can intuit that, for example, I have taught you some course. So instead of I have taught you some course and you need some intuition of that course. So let's say you have taken machine learning, you read machine learning and you came to deep learning. So a person who is directly coming to deep learning, he will take much time to understand deep learning. Rather, as you have taken machine learning course, that means as you have already pre-trained. So you will take very less amount of time to grasp all the concepts of deep learning. So that is what we do over here. So that is basically the importance of pre-training. If we pre-train, so that means the model will faster, it will show faster convergence rather than if a model is trained from scratch. Like a person is learning deep learning from for very beginning, or a person is learning is basically taking the course deep learning rather than he has previously taken a course of machine learning. So for him, it will be very easier because already he has pre-tuned or pre-trained. So the deep learning course is just a fine tuning for him. So this is kind of analogy for stack.autoencoder.
Okay, so then actually I got confused when what is the difference in deep autoencoders and then stacked, because both has a layer training, right?
Yeah, so actually we use these terminologies, we misuse these terminologies quite a way, because deep means, by deep you mean that you have very large number of layers. So that means deep means that, let's say over here I have 3 encoder layers. Rather, let's say you have 15 encoder layers. That means you will be having 15 such encoders, then 15 such decoders to get the output. That means a total of 30 plus 2, 32 layers. So that this basically gives you a flavor of deep learning. Now stacked autoencoder is also deep learning. This is also a deep network. Let's say you stack 10 layers. So 10 plus 10 plus 2 input and output. So 22 layers. So stacked autoencoder is a part of deep learning only. Until and unless in a stacked autoencoder you use something like this. So this I cannot say that this is a very deep network. Right, because you just have 4 layers. So this is not a very deep network. This is a shallow. So in literature, you will see this particular term, shallow network. You can Google search it. So the smaller networks, which are very small in terms of their depth, so these are called the shallow networks. But stacked autoencoder, it also comes under deep learning only, because you have a stack of several stacks of autoencoder only.
Sir, while earlier while explaining that stack autoencoder, you said that parallel training is fine possible.
Yeah, you
But
see
if
some
that is
of the,
so, Yeah, if that is so, stacking the layers, how come they are dependent then?
Stacking means after you pre-train them, you're stacking all together. Okay, so I'm not saying that while parallelly training, I mean this one. So let's say you are training this particular autoencoder, this particular layer like this. So you train it at once, then you store the weight values. Parallelly, I mean is that you give the input, you train this particular layer 1, layer 2 with another decoder layer, layer 3, another decoder layer.
Got it, sir. Again, it is normal autoencoder, right?
It is normal
Again, it is.
autoencoder only. We are just exploiting the GPU. So over there, in case of a GPU, you have multiple threads. So in each of the core, let's say you have a 8-core machine. So if you have 8 particular layers in the autoencoder, so in each of the core, you can assign each of the layer. So each of the layer will be trained parallelly. So over there, we exploit the parallelism of the hardware itself.
Okay, got it.
So if we have no further questions, then we can stop the lecture over here. So we'll meet on the next week as well. So try to submit the assignment before the due date, because still I see several people actually ask me that whether the date could be extended or not. So date cannot be extended. So you have to respond within the due date itself. So please submit your assignments before the due date expires.
Thank you, sir.